Hi there. Thank you for joining me on this series of videos that covers chapters 2, 3, and 4. And the very first thing that I want to say is that don't panic. It is only this week that we will cover this many chapters in a single week. Typically, it will be one chapter per week. But the reason why we cover these 3 chapters all in a week is because this really should be a revision from material that you have covered in your earlier courses. In particular, BIO201 or BIO156. So this is more like what we want you to feel about this week. Also, know that other than the weekly quiz and other assignments, this material as such is not included in your exams of this course because you have already been examined on it as part of the other courses, so no sweat. And on this video we will be doing a quick review of the basic chemistry as it relates to biology. So I guess that one of the typical questions that I get from the students is that I signed up to study human anatomy and physiology. Why do I have to study chemistry? And the answer to that is quite straightforward, I think. Since everything is made of chemicals, and this includes you, your body as well, it is chemistry and chemical reactions that underlie pretty much all physiological processes. So to understand biology, you must have some understanding of the basics of related chemistry too. And of course, these descriptions are just something silly and fun, not something that is factually fully accurate. But we like to have a little bit of a competition amongst the faculty on different fields of science, and especially with the physics folks. So let's get to the real topic here. What is matter? Well, matter is all the stuff that the universe is made of. And to be more precise, in the field of science, we have pretty good definitions for most things. So we would say that matter has 2 fundamental characteristics that we want to note. First of all, this stuff that we call matter must take up space. Think of a pen or a marker in front of you. It does take space in the universe. It is not just this abstract concept that we cannot define. It is very concrete, it has dimensions, substance that it is made of. It takes up space. The other thing to note is that all matter has a mass. And remember this from your physics classes. Although we often think of mass and weight as being the same thing, this is not the case. You remember the weight is dependent on the gravity. So example, although your mass, which is related to the amount of matter, is same both on the Earth and on the Moon, your weight on the Moon would be 16.5% of what you experience on the Earth. So if one weighs 100 kilograms on the Earth, this person would weigh only 16.5 kilograms on the Moon. What a way to feel better about yourself, right? I was just born on a wrong planet. And one more thing that I want to add to this slide is that we remember that of course matter can take one of these 3 forms, as solid, liquid, or as gas. Okay, the next thing that I want to discuss just quickly with you here is a short reminder of what energy is. So if we contrast that to the matter, which we just talked about, energy is sometimes a little harder concept for some of the students to get their head around. This is because it is less tangible. And typically the definition that we see for the energy is that it is a capacity to do work. So it is all about being able to put matter in motion. If you think about it, more energy is needed to get more work done. So it kind of makes sense, right? At this point, I do have to point out that although this definition is very common, and the one that your textbook uses, and therefore one that we will follow, I am going to be a little difficult here. Because I think that this definition, capacity to do work, fails by overlooking the fact that there is energy there, even if it's not freely available to do work or put things in motion. It is still there. So I wonder if it is all that great of a definition, but as it is the one that your textbook uses, it is the one that we will use. Finally, from this slide, I want to mention the two kinds of energy that you should be available of. Kinetic energy, which was all about moving objects, and potential energy, which is stored energy that has a potential to do work, but is not presently doing so. So, for example, these books on a shelf of my office have stored potential energy. They want to fall down due to the gravity, but they are not actively doing so. They just have potential capability to do so. Anyone who has helped someone to move to a new flat that is on a high-rise building knows how this carrying things like dishwashers up the stairs, right? But what can happen is that this potential energy that these books had, it can change into kinetic energy. Remember, this was energy in motion, such as this falling book has. So energy can be also transferred from one form to another. I just want to mention here quickly that remember that we can have many different forms of energy, chemical energy being especially relevant to us when we think, for example, the nutrition and digestive system. It is the energy stored in the bonds of chemical substances that we try to harvest by rearranging the chemicals and using it to drive our bodily processes. And whatever is stored then in the body, in the chemical bonds, we can then release when needed and convert into kinetic energy, for example, to drive our movement. Of course, electrical energy has one very obvious example to us. Think of the flow of electrons in the wiring all around your house. We generate this at the power plants, transport it, and then use it to power our appliances. But note that there are electrical currents also in your body. These are generated by charged particles called ions moving across or along the cell membranes. For example, our nervous system uses these currents, which we know as nerve impulses, to transmit messages from one part of the body to another. A good example would be the heartbeats being regulated by these currents, which rhythmic character is initiated by a special node in the heart. And this is why, if the system fails, a strong electrical shock can realign this rhythm. Well, I think that the mechanical energy is pretty obvious here. For example, when running, the muscles in your legs provide the mechanical energy that moves you along. And then we have electromagnetic energy, which is the type of energy that travels in waves. These waves can vary in length, and there is a huge spectrum of these, ranging from the visible light, which is what we see, to UV waves and X-rays. And of course, our eyes are the receptor organ that is specialized to receiving this energy and separating different colors, shapes, and other information from it. While UV waves can cause sunburn, but also play an important role in the processes behind your body making vitamin D. Finally, I do want to emphasize that we constantly have energy being converted from one form to another. We see this all the time, but with every transfer, which we see in this image as wiggly red arrows, every time there is some energy lost when we convert it from one to another form. And most commonly this loss is in form of heat. So let's take what we learned earlier about matter and take it a little bit further. All matter is composed of elements, which is what we will have a look at next. And basically elements are something that cannot be broken into simpler or smaller substances by normal, typically available chemical methods. And in fact, we currently know 118 elements, and 92 of these occur as they are in nature. For the rest, we must do some lab work to produce them typically. And of course, you have seen this weirdly shaped checkerboard, which is our periodic table of elements. It lists all the known elements and also allows us to deduct information of their properties based on the way they are arranged on this table. And there are 4 elements that are especially important to us. These: carbon, hydrogen, oxygen, and nitrogen make up 96.1% of our body weight. And then each element is composed of atoms. Let's have a look at these in a little more detail. For a long time, we thought that atoms are as small as it gets, but we now know that they are made of different parts known as subatomic particles. And I'm sure that you covered these in your introductory classes that are a prerequisite for this one. But as a really quick review, let's have a look at these. So the nucleus of an atom is made of protons and neutrons. Protons carry a positive charge while neutrons are neutral. So the nucleus is overall positively charged. And then around the nucleus we have electrons circulating on a shell. These are negatively charged. And the fact that the number of protons is equal to the number of electrons leads to the fact that all atoms are electrically neutral by default. And you remember that earlier we talked about elements. Well, different elements contain different number of subatomic particles, and you should be familiar with atomic number, mass number, isotopes, and atomic weight. If not, please review those from your earlier courses material. Okay, I think that we are now ready to look at what happens when atoms join together. So when 2 or more atoms join together, we have a molecule. And when these molecules are made of 2 or more different types of atoms, we end up with a compound. And different matters exist as mixtures. And we have solutions, colloids, and suspensions. Again, I would expect that you have covered these in your previous courses. The last topic that I want to address in this video is the 3 different types of chemical bonds that we have. And remember that much of the background for these is in the fact that some elements are more stable and some less stable, depending on the number of electrons on their outermost shell, known as the valence shell. Let's have a look at each of these in a little more detail, but remember, this is meant to be only revision. You should have covered these in your previous courses that preceded this class. So remember that in ionic bonds we have atoms that are both very reactive. They need to do only little changes to reach the happy place where their outermost electron shell is full. So these atoms are actively looking to get rid of or gain one or few electrons. So here we have sodium atom that has only one electron on its outermost shell. So it will want to get rid of it in order to have the next shell as its outermost, and this one is full, so the atom would be in a happy place. And in this example, we also have a chlorine atom which has 7 electrons on its outermost shell. So it is going to want to gain one more electron to reach full outermost shell. So what are they going to do? Well, of course, it would make sense for these to proceed by sodium donating only one electron from its outermost shell away, and for the chlorine atom to receive it. Both would be happy, right? So let's say that this happens. Now we have managed to get both of the atoms happy, right? But we have a bit of an issue to tackle. We remember from earlier that normally atom had a same number of protons and electrons, right? But now we end up with the sodium having one less electron than it has protons. And as electrons were negatively charged and protons positively charged, now overall the sodium is going to be slightly positively charged. And the same, but in reverse, is true for chlorine. It will have more electrons than protons, making it overall slightly negatively charged. Well, it just happens that opposites attract each other. And as a result, positively charged sodium and negatively charged chloride join together, forming sodium chloride. This is, of course, what we know as stable salt. In fact, most ionic compounds are salts. Now, let's look at covalent bonds. In this case, atoms are still looking to have a full outermost electron shell, but instead of completely handing over or receiving electron, an electron is shared by two atoms. Let's look at an example of this. So here we have 4 hydrogen atoms, and for each one of these to get a full electron shell, each one would need one more electron on its outermost shell. And we also have 1 carbon atom, and we see from the diagram that it has 4 electrons on its outermost shell, so it would need 4 more to be happy. But in this case, no one is going to give or receive an electron fully. Instead, what happens now is sharing. After all, sharing is caring. And what we get is that each of these hydrogen atoms shares one of its electron with carbon atom, and in exchange of this carbon atom sharing one of its electrons with each of these. And now everyone is happy. Each hydrogen atom has 2 electrons on its shell some of the time. And the carbon has 8 electrons on its outermost shell some of the time. And now what we have formed is known as methane gas. Finally, let's look at hydrogen bonds. When we compare hydrogen bonds to the 2 previously addressed types of bonds, these are not really true bonds as such. Instead, hydrogen bonds are more like attractions. These happen when a hydrogen atom already covalently electrolinked to one electronegative atom is attracted to another electrohungry atom so that a bridge forms between them. So this is what we see with water molecules tending to stick together. And this is what gives the water its high surface tension, which again is used, for example, by this bug that we see walking on water. So these are our 3 types of chemical bonds that you should be familiar with. And this is the end of this video. On the next video, we will finish off this chapter by looking a little bit of the biochemistry. As I said, all this should be a revision, so you should be fairly comfortable with it without us spending too much time on these topics.